Right, so this is the last lesson in Chapter 5, just continuing the ideas that were started in the last lesson, which is especially looking at the connection between graphs of linear relations and their equations. And so, again, the coefficient of x is the average rate of change, or the slope, and the constant is the fixed cost, the starting point, the y-intercept. And I have one example here looking at the relationship between air temperature and altitude above the ground. And in general, as we can see from here, the higher you go up above the ground, the colder the temperature gets, which you may have noticed if you've paid attention to the temperature. If you're on a plane outside, it's very, very cold when you get quite high up in the air. So from this, I want to find the equation of this line and then use that equation. So first thing again, any equation like this can be written in this form, y equals ax plus b. A few things though, instead of having y and x, I have altitude and I have temperature. So I'm going to pick A for altitude. I'm going to pick T for temperature. Actually, I use a capital T. A little more conventional, doesn't really matter. And so I'm going to go to my equation and change that y to a capital T for temperature and change that x to A. Oh, that's a little confusing. A for altitude. Let's go with h for altitude, h for height. All right. However, soon enough, I won't have these variables a and b. I'll figure out what they are. Okay, so with that said, it's not wrong to have x and y, but we want to be clear what these variables represent. And generally, there's better choices than x and y to use once they actually represent something. So the first thing I'm drawn to is the y-intercept, where this graph crosses the y-axis, or the time axis. Sorry, not time axis, the temperature axis, I guess you could call it. And I can see it's at 21. That means it's 21 degrees at sea level. When the altitude is 0 and the height above the ground is 0 meters, which means you're right on the ground, the temperature outside is 21 degrees. That's what this is telling us. And so my equation I can now write as T equals A times H plus 21. And again, if that h is throwing you off, you'd rather have an x, have an x. Just know that your x-axis stands for the altitude, or the height above the ground. And now, what's the slope? What's the average rate of change? Well, there's only two nice clean points I show you on this graph. That's all we need. And so what I'm going to do, which is I'm going to make a quick little simple table comparing, in this case, height and temperature with just these 2 points. So what do I know? I know when the height is 0, the temperature is 21. When the height is 3,500, the temperature is 0. Okay, so what's not immediately useful to me is that I can see that as the height goes up by 3,500 meters, the temperature goes down by 21 degrees Celsius. I say it's not immediately helpful because it is helpful. I don't need any of those numbers. I need to kind of work with them. I need to use some proportional reasoning and realizing, okay, I want to figure out as height goes up by just 1 meter, what does the temperature go down by? I know it's going to go down, but by what? Well, if 3,500 meters brings us down 21 degrees, just going up by just 1 meter, I know it's going to be a small amount, which makes sense. If you stand on top of a chair, it's not like it starts snowing. And so it's going to be a small amount, but how much? Well, 21 divided by 3,500. And so I go to my calculator and go 21 divided by 3,500. And I get 0.006. Or as a fraction, I get 3/500 if it reduces. That is my average rate of change. And honestly, I like the decimal one better because I can see a little more clearly that on average, every 1 meter we go up, the temperature drops this tiny bit, 0.006 degrees Celsius. But the fraction is great as well. And so my equation I'm going to change to T equals negative 0.006 H plus 21. And like before, did we really need the table? No, we could have figured that out from looking here, realizing I go down by this much, and when I go over this much, and kind of proportionally realize it to just what happens as I go over just 1 meter. But in general, I'd always recommend a table if you're not sure. But now I got the equation here, so now let's use it to determine the air temperature at an altitude of 10 kilometers. So my equation here is set up to think in meters. If you look at the graph, everything's in meters. And so 10 kilometers, we just got to think, okay, what's 10 kilometers in meters? Well, 10 kilometers is the same as 10,000 meters, because 1 kilometer is 1,000 meters. And that is what I want to put into my equation for the height, or the altitude. And so now the temperature is going to be negative 0.006 times 10,000 plus 21. And that's really the most important part, but being detailed, go to the calculator, so negative 0.006 times 10,000 plus 21. And according to our model, it's negative 39 degrees. So 39 degrees below zero, 10 kilometers up in the air, which actually is quite reasonable. Again, you go up that high, I don't care where you are in the world, it's cold. And again, that's just based on our model here. All right, really key ideas. And remember again, as in the last few lessons, the tables are not essential, but they're always a good starting point.